Hey everyone, welcome to this class 17a. Today we will talk about special partial derivatives that are related to useful coefficients in thermodynamics that describe the compressibility, the thermal expansion, and the specific heat of substances. In the meantime, I hope you're still doing well and you're able to cope with the whole situation, the lockdown, and we realized that we are putting a lot of responsibility on you guys to do the teaching mostly yourselves. Of course, we provide the slides, but it's up to you to actually open the video lecture and listen to it and try to absorb as much as possible. So we hope that's going well. If you somehow experience problems with that, or if you think that things should be done in a different way, please don't hesitate to let Wout or me know. Well, before we start off with this new class, let's give a short recap of class 16b, the previous one, where we learned about the Maxwell relations, which can be obtained from total differentials, like the one here for the internal energy. And we learned about this trick. We can look at the first term. We can take the partial derivative of t with respect to v for fixed s, and we get one partial derivative, and that is then equal, as we showed mathematically, to a second partial derivative, which we obtain from taking this in the second term, the derivative of minus p in this case, with respect to s for fixed v. And this is in fact one of the Maxwell relations that we derived. And we derived four of them in total from each of the fundamental thermodynamic energies. We derived one Maxwell relation from the internal energy, from the enthalpy, Helmholtz energy, and the Gibbs free energy. We got all these relations. And we furthermore saw a few things about phase diagrams, PT phase diagrams, where Wout showed how, from a qualitative understanding, you can tell where the phases should be in this PT diagram. We learned about triple points, critical points, and we learned about the Clapeyron equation, which relates the slope of this specific curve, the saturation curve, to the enthalpy of the phase transition. For example, the enthalpy of vaporization when you go from a liquid state to a vapor state. And we also saw that we could simplify the Clapeyron equation a bit by getting rid of the specific volume, which is actually the difference in specific volume between the two phases during the phase transition. And making a couple of approximations, we got this slightly simplified expression, the so-called Clausius-Clapeyron equation. Now, at the end of the previous class, we looked forward towards well, basically this class, and we kind of promised that we would show you a way to derive any of the 500 remaining partial derivatives. But Wout and I decided to move this actually to the next class, 17b. In this class, however, we will still look at some of these partial derivatives, and we will see how they are related to very useful properties like specific heat capacity, expansion coefficients, and whatnot. And there will be a movie by Wout where he will show you a couple of, well, he will show you how to derive a few of these coefficients from an expression, a total differential like this. And after the movie, we will take a closer look at specific heats, which is something that we encountered already in class 3. And we will, well, apart from looking at their definitions, we will also learn about the relation between these two different specific heats, Cp and Cv, the so-called Nernst-Lindemann or Mayer relation. Okay, in the last video lecture, we also promised that we would explain why some gases cool down when they undergo adiabatic expansion, whereas others warm up, which is the so-called Joule-Thomson effect. And also this we decided to move to the next class. So this class will focus basically on what's within this frame here.
Dear students, welcome to another video. This video is about class 17A, defined partial derivatives. I'm going to tell you about partial derivatives named alpha, beta and kappa. Let me start with my bag of crisps again, which we still remember from the first video. And this bag of crisps had a certain volume, V, and this volume depended on pressure and temperature. And we wanted to bring this bag of crisps up into the mountain so the temperature is lower and the pressure is lower as well. And back then we saw that the volume increases due to the decrease in pressure. Well, and of course, it's the contents of this bag of crisps is treated as an ideal gas. Ideal gas. And actually, now I'm very interested in the behavior of this change in volume, so dV, divided by its volume, by the initial volume, V. And I'm interested in this since for the material of the bag of crisps, it's interesting to know how much what the percentage of increase in volume is with respect to its original volume. So, and I'm going to, well, define this by using the original derivative of the volume, which is the partial derivative of volume with respect to pressure, dV dP. So the partial derivative for fixed temperature, delta P, plus the partial derivative of volume with respect to temperature for fixed pressure, dt. And since I have this 1 over V of this volume over here, I need to put the 1 over V in front. 1 over volume. So move this one plus 1 over volume. So this is my basic equation. And since it's hard to keep both, since it's very hard to keep both of them into account, I'm going to examine those this total derivative divided by the volume one by one. And for this, it's useful to have a little bit of knowledge about the behavior of pressure over here and temperature and volume over there. So how does the pressure and volume relate to each other? And we know that it is an ideal gas. So PV is RT. So the pressure behaves like RT over V. So actually it behaves like the pressure is a constant divided by the volume. So it's a 1 over volume behavior, and it looks like this. And this is of course for a constant temperature. So this is an isotherm. So the temperature is constant. Okay, and that's exactly what I'm going to do. I'm going to calculate this partial derivative, assuming that the temperature is constant. So T is constant. And from that I know that dt will be 0. Well, and solving this will lead me to dV over V is 1 over V, the partial derivative of volume divided by pressure for a fixed temperature, dP. And from this, I can actually say that this part of the integral of the differential is equal to the of this is called the isothermal compression coefficient. Or actually not this. I'm joking a bit. This is called the isothermal 1 over V dV dP for a constant T is equal to kappa. And this is called the isothermal compression coefficient. And let's have a look at this. Because the volume with respect to pressure, if I increase the volume, the pressure will decrease. So my kappa should decrease for a increasing volume. So there should be a minus sign in front. Okay. Okay, so this is the isothermal compression coefficient, and it's named kappa, and you should keep it in mind. Okay, let's assume I have a flooring, and in between this flooring there's a heating system. So in Dutch it's called vloerverwarming. And of course, when we put hot water in, or maybe it's electrical heating, then the floor will, of course, the whole thing will expand. And that may have effects to my floor. So I need to take these into account. And I'm going to do this by assuming that the pressure is constant. And I think it's a fair assumption because there won't be a lot of pressure loss in these pipes. But temperature will definitely change over the pipes. So I'm going to take into account the change of volume, dV over V, for a constant pressure. So dP is 0. And that will look like this. dV over V is equal to 1 over V, partial derivative of volume with respect to temperature for a fixed pressure dt. This coefficient over here is called, well, its name is beta, and it is called, and I will write down the definition to make sure you got it right, dt for fixed pressure, and it is the thermal expansion coefficient. So for constant pressure, change in the change due to thermal effects will be described using this defined partial derivative. Well, and then there's another one, and that one is actually very interesting. For instance, when you inflate the tires of your race bike, of course, in the first part, this one is really important, the change in volume due to pressure. But when the volume, when the tire is up to pressure, volume won't change a lot anymore. At the when you go, for instance, from 4 bars to 8 bars, the volume won't change anymore, but the pressure will. And for that, I'm very interested in this derivative, dP, difference in pressure with respect to its original pressure. And to get this derivative, I need to take this equation into account again. But now I'm going to, well, and I have to derive this equation. I'm going to do that using this equation. dV is dV dP plus dV dt, and this is for a constant pressure, and that's for a constant temperature. And actually, I want to determine this one, since that one is over here. So I need to isolate this one. So I'm going to divide everything by dV dP and get this one to the other side, to the left-hand side. And that will result in this equation. I'm going to write it down over here. And I don't remember it by head, but it will look like this. dP, and you can check it for yourself, of course, minus delta V by delta T divided by delta V over delta pressure for a fixed temperature dt plus 1 over delta V divided by delta P for a fixed temperature dV. And this one is for a fixed pressure. Okay, now, because this looks very complicated, it's not very useful, and actually these defined partial derivatives are very useful, so I want to get to a useful equation, and that's why I need this equation. So I'm going to plug it in and especially apply it over here, and that will look like, that will end up as dP is equal to dP dt for a fixed volume multiplied by dt plus dP dV for a fixed temperature multiplied by dV. Okay, like I already said, at a certain pressure, the volume, the shape of the tire won't change anymore, or will remain more or less constant. So I can say, well, the volume is constant, so dV is 0, so this one drops out. That will lead me to this equation. dP is equal to dP dt for a constant volume dt. And now I'm going to divide everything by the pressure. So the original pressure is 1 over P. And this will lead me to my last coefficient, which I'm interested in. So it's this one. And that one is called alpha. So 1 over P dP dt for a fixed volume, and this is called alpha, and that's the isochoric pressure coefficient. So all of these coefficients can be used to make writing a little easier, to make mathematics a little easier, and can help you to define the material of the bag of crisps, the amount of space you need to mount into your floor to prevent it from cracking the floor for your floor heating system, or depends the rate of pressure increase for your bicycle tire. Well, I wish you good luck with the next part of the lecture, which will be about thermal heating coefficients. Thank you for watching this video.
So that was another interesting and very clear movie by Wout. So we learned about the thermal expansion coefficient, beta, and there are actually applications. So Wout already mentioned so-called underfloor heating systems, where you have your expensive, well, we call it laminate, your floor. It can be a wooden floor even, and then you have this heating system, and then, well, there's typically some concrete at the bottom, and you don't want things to get squeezed in between heater elements that are expanding and make your floor buckle. So you have to design it carefully such that it can handle all the deformations and thermal expansions. Um, Speaking of buckling, if railroad tracks get too hot, uh, they will also start to bend and buckle. And in principle, railroad tracks have little gaps in between different segments. At least that's what I've been told. But if temperatures get too high, then even these little gaps are not enough, and then you get disastrous results like what you see in this picture here. Um, what else can you do with thermal expansion? Well, maybe you've seen bimetallic strips, which are two layers of different metals with different expansion coefficients. And if you heat these, they will start to coil up, for example, like you see in this animated GIF. Um, so it's a way to convert thermal energy into mechanical energy or into motion. And this in turn has been used in, for example, this clothes iron, which is being heated until the temperature becomes so large that this bimetal strip bends and it breaks the electrical loop, the electrical circuit, until it cools down and it closes the loop again, and then the whole thing is heated again. And in this way, you can kind of regulate, control the temperature of the iron. And last but not least, here's a very famous example. And as a matter of fact, when I was looking at this while making these slides, I realized for the first time that this thing is not a thermometer. This thing is just a ruler. It measures the length of a mercury column, and the length of the mercury column changes, of course, with temperature, and you're measuring the length change, and the scale of the ruler is calibrated such that it is translated to temperature. Um, okay, maybe some of you guys have had this insight ways many years before, but for me, that was the first time yesterday, and it was really an eye opener. Okay, as already announced by Wout, we will also talk about heat capacity. So what is heat capacity? Well, it's basically the amount of energy that you need to warm up a certain amount of substance by a certain temperature, or a certain increase of temperature, I should say. And this is sometimes denoted by capital C, and it's an extensive property with units joule per Kelvin, and it depends, of course, on the amount of substance or the mass of the substance that you are considering. Um, then, of course, you can also define a specific heat capacity, or sometimes just briefly specific heat, which is the intensive variety of the heat capacity, which has units of joule over kilogram times Kelvin. Now, specific heats, they depend, well, first of all, on the substance, the element that you are considering, but it also depends on the process that is involved here. What I mean by that, you can, for example, define a specific heat capacity for a constant volume process, and this is defined as the change in internal energy with respect to temperature for a fixed specific volume. That's the definition of the specific heat capacity, CV. And one way to realize a system that demonstrates this is, well, you can take this piston cylinder. Uh, the piston which normally would be free to move through the cylinder, is now blocked by a stop. And inside there is a gas, and there is an equilibrium. There's a balance between forces. There's an outward pressure by the gas trapped in here, and there's also the atmospheric pressure pushing onto the disc, onto the piston from the outside. And if we now add heat to this gas, then something will happen. Uh, in this case, the volume is not going to change because it's fixed. The pressure will increase, but the volume will not change. And in this case, the heat capacity that you need to use is CV, as opposed to the situation where you add heat under constant pressure. In that case, you need to work with the specific heat capacity Cp, which is defined as the change in enthalpy with respect to temperature for a fixed pressure. And of course, you want to use enthalpy here because this change in energy now does not only involve a change in U, like here, but it also involves a possible work that has to be done, flow work, for example. And to illustrate that, here's again a piston cylinder, but now the piston is free to move, and we make sure that we have the same pressure, the same amount of gas, and we have the same pressure by adjusting this weight here. And we again add the same amount of heat. Now, when the whole thing heats up, the pressure here becomes higher than, or the force on the piston from this side increases. It will become larger than the force from the outside direction. So the entire piston will be moved over a certain distance, and this is actually work that is done. So the amount of heat that we are adding cannot be fully converted into the motion or the temperature of the gas, but some of the energy actually has to be used to move the piston and do the work. And for this reason, the specific heat, Cp, is usually larger than Cv. What I mean by that is to achieve a certain temperature change, delta T, of your gas, for example, you need to supply more energy in the case of a fixed pressure because you have to do this additional work. This is delta W, which is in this case the pressure times the volume change. And as you will see in exercise 7.2D in the watt reader, the difference between the two can in some cases be astonishingly simple. In this case, if it's an ideal gas, then Cp minus Cv is just equal to the gas constant. Now let's take a closer look at the definitions of Cv and Cp, and let's start with Cv, which is valid for a constant volume process. And we had seen this definition here already before on the previous slide. So we're talking about processes that are isochoric, that have no change in specific volume. Now let's write down the total differential of the internal energy expressed as a function of entropy and specific volume. Well, by now everyone will know how to write down this total differential in terms of partial derivatives. And since this is an isochoric process, this term becomes zero, and we basically have we only retain this term here, which is equal to the TdS in this side of the equation. So this is basically what we find for an isochoric process. Now what we can do is we can take a partial derivative of u to t. And at first sight you may be wondering, wait, u is not written as a function of t, it's only written as a function of s and v. So how can we take a partial derivative to t? Well, in class 15b, if I'm correct, you learned about a trick that's called the chain rule. if you have a partial derivative, for example, du ds, you can split that into, or you can write that as a product of one partial derivative du dt times dt ds, which is then equal to this partial derivative here, or this one. So you introduce this, well, we called it a dummy variable, but in this case, it turns out to be very practical because we can first, in the first step, write this expression here. This is basically this partial derivative written in this form with the help of the chain rule. That's equal to t, and now we can use the reciprocal relation of partial derivatives, where if I take one divided by a partial derivative, well, you can just use it as a normal a fraction. So we can take the dt ds to the other side of the equation, and this is then what we find. We just divide both sides of the equation by dt ds. Now, what we have found here is an expression that relates the heat capacity, specific heat capacity, with entropy changes versus temperature. That's interesting because we have always been told that entropy changes are difficult to measure directly. And this gives us a connection with something that is something from, this is a coefficient from the real world. You can determine this yourself if you want to. So this is then basically a double definition of the specific heat at constant volume. This is the first definition that we saw, and it turns out you can also write it in terms of entropy changes with changing temperature. And in all cases, it's for an isochoric process, so no volume changes. Now, for completeness, we of course also want to take a look at the specific heat at constant pressure, for which we have a slightly different definition. In this case, we started out from the enthalpy instead of the internal energy. And we consider isobaric processes where the pressure doesn't change, where dP is 0. Since we are starting out from the enthalpy, we want to write down the total differential for the enthalpy in terms of S and P. Well, dP is 0, so this drops out of the equation. So we end up with this simplified expression. And then we're going to take again the partial derivative of the enthalpy with respect to the temperature, for which we again use the chain rule and the reciprocal rule. And then we end up with this definition of Cp. The first expression here is our original definition that we also have here. And this here is a useful relationship with changes in entropy, the partial derivative ds dt. And this is almost the same expression that we saw on the previous slide for CV, that was equal to T times ds dt, but then for fixed volume, and in this case it's for fixed pressure. And so again, another interesting relation that we can use later on. Now, as a matter of fact, it turns out that the specific heat CV is difficult to measure. It's easier to measure Cp, which is the one at constant pressure. And now we're in the lucky situation that we can actually express CV in terms of Cp, and also these coefficients beta and kappa that Wout showed in his movie, the compressibility and the thermal expansion coefficients. And you see this expression here. This is the Nernst-Lindemann or Meyer relation. And the derivation of this expression we postpone to exercise 7.6 of the Watt reader. And this is the name of this relation is in honor of another few great minds of the 19th century. So thank you, Mr. Meyer. We're still using your insights today in 2020. Now you can also show that for an ideal gas, this quantity here uh, simplifies to the gas constant R, and this gives a relatively well-known relation between Cp and Cv, which we also saw early on in this video lecture, namely that Cp minus Cv equals the gas constant. And for an incompressible substance, it turns out that this factor here is 0, which results in Cp and Cv being equal. And that's also in agreement with what you would infer by looking at their definitions and thinking about it in a logical way. Now here on this slide, you see a derivation of what we saw on the previous slide, that the Nernst-Lindemann equation, this guy, simplifies to this one, Cp minus Cv being equal to the gas constant for an ideal gas. So you may want to pause the video for a minute and walk through the derivation yourself. And now to conclude, just a few more words about the Nernst-Lindemann or Meyer relation. Let me bring out my pointer again. So this was the relation as expressed in all these different coefficients. What can we tell by looking at this equation? Well, first of all, we know that Cp is always larger or at least equal to Cv. And we can also judge that from this side of the equation, because we know that all these coefficients and the temperature and the specific volume, these are all quantities that are larger than 0. So that's another way of telling that Cp is always larger or at least equal to Cv. Another thing we can learn from this equation is that if the temperature goes to 0, then apparently Cp starts to approach Cv. That's another conclusion that we can draw here. And then, well, we talked about incompressible or nearly incompressible substances. We know that in that case, the volume doesn't change in either case, so Cp and Cv should be basically the same, which means that this quantity here should be very small. Now, in the extreme limit of an incompressible thing, then this kappa goes to 0, but beta also goes to 0, and it goes to 0 basically twice as fast, because it's a square of something that becomes very small. So this guy wins over this one, which tends to blow up this number or this fraction. And you can also try for fun just to look up the beta and kappa coefficients for example, for water, and combine it with the temperature at room temperature and the specific volume to see if it matches up and indeed confirms that Cp and Cv for liquid water is indeed, well, that these two are almost the same. And then here to the right, there, well, it's basically a simple depiction of what happens if you have a piston cylinder filled with 1 kilogram of a substance. In the top panels, it's a substance with a large beta coefficient, which means that if you heat the substance by only 1 degree, then there's already a huge expansion, huge compared to the case where you use another substance that has a small beta coefficient, which leads to a much more modest expansion of the substance. And this increase in volume, this partial derivative here, is of course linked to beta, but it's not exactly the same thing. What is shown here is the so-called volume expansivity, or also called the coefficient of volumetric expansion. So these classes were all about mathematical tools. So what are the tools that we learned to wield so far? Um, well, we've come across the different thermodynamic energies or thermodynamic potentials. Uh, we have seen how we can derive Maxwell relations, and we have also seen and today even used a number of mathematical relations between partial derivatives, like, for example, the reciprocity or reciprocal relation and the chain rule. Now, the goal of all this was to primarily express quantities which are difficult to measure in terms of quantities that are readily measured. Um, and today we saw a few interesting examples of that. Uh, for example, the specific heat, um, where we could relate the CP, which is something that is, or I should be looking at this one, CP, which is something that we can relatively easily measure that can be related with changes in entropy, for example. And we've also seen how these partial derivatives can connect to very real physical properties like expansion coefficients or compressibility coefficients. So coming up in the next class, 17b, we will finally learn about this long-awaited general method to derive any of the 500 remaining partial derivatives. And we will also understand why some gases cool down while they undergo adiabatic expansion, and sometimes they warm up, which is related to the Joule-Thomson effect. And it's one of the phenomena that allows you, for example, to cover skiing slopes with snow, even if there's no snow falling from the sky. Now, the image of this slide has probably been burned into your memory by now. As you may have noticed, we're also distributing a PDF version of the slides of each video lecture, and you might find it handy to have these formulas at hand at the end of each separate slide deck. So that's one reason why we also keep them in each video lecture. And again, many thanks to Genie Stoffels for letting us use and edit her slides. And last but not least, here's another attempt to store things in your long-term memory. And this time we're going to do it again a little bit differently. I would like to ask you to take a minute and try to remember at least 5 of the coefficients we have seen today. And if you can't remember them, then please look them up and memorize them. And as always feel free to approach us if you have any questions or comments or suggestions for improvement. Okay, see you in the next online session.